Hi everyone. This is Mechanics, M1 paper from summer 2014. So we're going to start off with quite a simple question. This is really just testing that you know what power is. So we know that the power exerted by something is the energy per unit time. Strictly speaking, it is the derivative of the energy with respect to time. So a watt, I mean, that's just joules per second. That's the unit. So what we have is power exerted by the engine on this train and some kind of resisting motion. And we're trying to see what the speed will be. So the other key fact here is that the work done by the force is the force itself times the distance over which it's exerted along the line of the force. So here we're dealing with one-dimensional motion, so we don't have to worry about things being along the line or not. But usually this would be a vector equation, and W and D have to be along the same direction, just scaled by this, W and F, just scaled by this factor D. So if we look at this situation, we notice first that the train is moving at a constant speed, V. What this means is that all of the work that's going in is combating the resistance to motion. It's not accelerating, so we don't have to worry about the division of the power between those two things. So here, this is an energy. That's an energy that's being exerted. So the power, we can just put this into the power equation, say the power is force times distance over time. But what is distance over time? Well, in fact, why don't I be much more formal, much more rigorous, and say this is going to be, so if we plug this in for the energy, we get, the force is constant, so the force just comes out, and then we get actually I shouldn't call it D, I should call it X, as in displacement, X. So dx dt, so that's just me plugging this into there. Well, what is dx dt? It's V. And that's all you need to do. So V is equal to P over F. If you plug the numbers in, you'll get the correct answer. Okay, so now we have a ramp question, ever popular. So here's our situation. Always draw a diagram unless you're very confident. So I'm going to call this angle here alpha. We will need it. And we have our box sitting on here. So again, the biggest thing with these questions is resolving it's called resolving when you split a vector up into components. You resolve this weight vector, so pointing straight down, you resolve it along these two perpendicular directions. And you get this little triangle there. And you can work out, and you should just memorize that is also going to be alpha. So you can work out with alternative angles and stuff. Now the normal force always points normal to the surface, at right angles to the surface. Opposite, and it balances this component of the weight. So we know that the normal, n, that one, must be equal to this component. So if the hypotenuse of this triangle is mg, and that angle is alpha, then this must just be mg cosine alpha. And we know they must balance, otherwise the thing would move. If you have an unbalanced force, the thing's going to move. And we're not told that it's not hovering above, it's not leaping off the surface of the ramp, and it's not sinking into the ramp. It's just, in this direction, is completely at rest. So therefore, these forces must balance. Well, maybe alpha doesn't, it's not given alpha in the question, but what you are given is m, we know g, and we know n. So alpha is just going to be the arc cosine, the inverse cosine of 2.4 over 2.5, right? Just solving for alpha, no problem. Now they're asking us about friction. So if we look at this situation, there is no force pushing the thing up. So any movement that takes place, you know, the sort of impulse of the block to move is going to be downhill. And therefore any frictional force, which might stop the block from moving or at least slow it down, is going to be therefore acting uphill. So they're asking for how the smallest amount that the friction coefficient can be to stop the block moving. Well, that means the friction that's required to balance exactly the component of the weight that's wants to move the block down the hill. So that component is mg sine of alpha, and that must be equal to the force of friction. Well, the force of friction is just mu n, where mu is the coefficient of friction. So we have all this. We have the normal force. You can solve for mu. This is a very easy question if you like vectors. So again, we're resolving all of these forces. They're vectors. You know, so they've got a magnitude and a direction. They're vectors, and so you can resolve them along perpendicular axes. So I've decided to choose this to be the y-axis and this to be the x-axis. And we just do it by component. So let's look at the net force acting in the x direction. Well, I have a positive, so I'm defining this as my positive x direction going to the right and my positive y direction going up. So I immediately have a 5 Newton force in the positive x direction. Great. Well, what about the 7 Newton guy? Well, he's not pointing along the x-axis, but he does have a component like so, which has a magnitude equal to 7 cosine of 60 degrees. And this you will know is one of your standard triangles. And the same with this 3 Newton force. This is a right angled triangle. It has a component in the x direction, so we subtract that, minus 3 cosine of 30 degrees, and that's the same triangle. This force doesn't have any effect in the x direction because it's completely along the y-axis. And you do the same with y. Fy, this 5 Newton force doesn't affect it. This one has, it's upwards, its y component is in the positive direction, so it's plus 7 sine of 60 degrees. And this one, it is pointing a little bit downwards, that's where its component goes. So it has to be minus 3 sine of 30 degrees. And then this last one is pointing completely down in the y direction, so we have a minus 4. And that's all you need to know. Now they want you to give it in terms of magnitude and direction. So really, this thing is just a vector. This is a vector of fx, fy, where each of these, you could just think of it as adding up the vector. So this vector is 5, 0. This vector is 0, 4. This vector is 7 cosine of 60, 7 sine of 60, sorry, yeah, minus 7 cosine of 60, sorry, and so on. So you can think of it also as these are all vectors and we're just adding them all up and we end up with a vector. So we've got fx, fy, and we want the magnitude of that. We just take the magnitude of the vector like we ordinarily do. So the magnitude of our vector f is the square root of fx squared plus fy squared. Now what about direction? Well, this is very easy to extract. There's a formula for it, but I'll just show you where that formula comes from. So direction, they tend to say, you know, like so many degrees from something. So usually we define that to be the positive x-axis. So we'll say, you know, if the resultant force was going like that, we would say, oh, it's theta degrees anti-clockwise from the positive x-axis. Positive x-axis, not negative x-axis. So to find this out, we realize that if we have, you know, some force, so here are our axes again, here is some force. This is just this bit down here is the x component of the force, fx. And this component here, well, that's just the y component of the force, right? That's the whole idea behind all of this. So if I want theta, and I've got the lengths of two sides, what do? Well, it depends on which sides. In this case, it's the opposite and the adjacent. So we use the tangent. So we know that the tan of theta is equal to Fy over Fx. So therefore, theta is just the arctan, or tan to the minus 1, or whatever, of Fy over Fx. And that's how you get it. Question 4. So this is one of these parabola equations. What do I mean by that? I mean that any question where something is thrown vertically up into the air and then comes down again traces out a parabola in the position time graph. So even if it's going straight up and down, it's not moving in a parabola in space, but it'll look like a parabola. So this is time, and this is, I'll call it y for vertical distance. So it initially starts at some non-zero vertical distance. Then it's going to arc up in a parabola and then come down and eventually hit the floor. So this parabolic motion, this is true no matter what the mass of the object is, which is actually a very profound result which influenced Einstein a lot in general relativity. But this thing is purely a factor of the gravitational field strength around it, which is what you mean by g, the gravitational acceleration, and the initial speed and the distances and things. So I'm going to do a little preparatory work and select this point specially. And I'm going to say that this point occurs at a time t prime. And this is the crest. So this is when it's at the very top of its motion. So it's traveled as far up as it can, and it's been completely decelerated. So at this point, the velocity, which of course is the slope of this graph, is 0. I'll call that v prime is equal to 0 at that point. So what can we get from this? We can use our constant acceleration equations, and we know we can because the only thing accelerating this thing is the force of gravity, which has a constant acceleration, g. So we can use the constant acceleration equations. So let's use the one for velocity. So I'm saying v prime, which is equal to 0, is equal to v naught plus acceleration times time, right? So that's one of our v naught being the initial velocity. Sometimes you see it as u. I prefer v naught. This you're very familiar with. So we can find out what t prime is. So that's t prime. We're talking about a specific time. We know v naught. We know a. I'm defining the y direction positive as being up. So therefore, the acceleration is equal to minus g because g acts downwards. And we have to give a sense of directionality. Otherwise, this would be accelerating positively and getting faster going up, but it's not. It's slowing down. There's deceleration. The acceleration is negative. So we can work out that t prime is equal to, oops. You can just solve for it and you get 0.9 seconds. Now the distance traveled, this bit here, the distance that they've traveled, sorry, not that bit here, between being launched and reaching this crest, s prime. Well, this is actually s prime plus 3.15 because I'm just looking at the distance between here and here. So s prime is equal to initial velocity times t prime minus 1/2 g t prime squared. That makes sense, right? This is the initial velocity times time minus 1/2 times acceleration t prime squared. So if you plug all that in, you get 4.05 meters, since we know t prime. Therefore, we can get the total distance that's traveled. So when it starts from here, it goes all the way up here, and then it comes down. And so that's 2 copies of this distance, right? And then it goes down to the floor, which is an extra 3.5. So total distance is 2 times 4.05 plus 3.15. No problem. They're also asking for the total time taken. For this, it's best to look just at this half of the graph, because this is super simple motion. You're starting with 0 velocity at some height, which we know, and you're just getting accelerated by gravity until you hit the ground. No problem. So you have the distance, which is that we're traveling between here and here. So not the total distance traveled, but just from the top to the floor, which is going to be 4.05 plus 3.15, so this distance. We have that this distance is equal to initial velocity, which is v prime times t. Well, that's just 0. Plus, now here it's going to be 1/2 a t squared, right? But the little subtlety I'm introducing is now I'm talking about distance, like it's traveling downwards. So I'm sort of reversing my convention. Otherwise, you'll get a negative distance, which might confuse you. So I'm just going to say that now that it's sort of traveling downwards, g is, we're going to give plus g. So it's 1/2 gt squared. And this, you just solve for t. It's going to be equal to 2s over g all square rooted. We know s, we know g, you get t. Okay, question 5. Okay, this is another ramp problem, essentially. They just stretched the ramp out annoyingly, so it makes it hard to draw on. I'm going to draw it again, am I? Yes. Or maybe I'll just do my best with this. So I'm going to call this angle theta, because I like to have an angle to work with. The first question is asking you to compare energies. And that's fairly straightforward. The only subtlety comes from the fact that there is some work being done. So it's not just a smooth ramp. It's not just a difference of potential and kinetic energies. You have work dissipated by friction, basically. Whether to the ramp or inside the car, there's some work being dissipated. So we're looking for the energy difference. So our system that we're considering is the car. We don't really care if the ramp gets some energy or whatever. It's about what the car has lost, rather than who's gained the energy. So we're looking to compare the energies purely for the car. So we have some delta K, change in kinetic energy. Well, it started at rest, and at some point it's now got some velocity v, so delta K is just 1/2 mv squared. Delta v, potential energy, well, that's just mgh. And we are not told h, but we're told that it's traveled x along the ramp. So up there. So this is x. Well, if this is h, then we have that h is equal to x sine theta. And theta, we know from, in fact, we can use the big triangle, which has the same theta angle. So we know that the sine of theta is equal to x, and the sine of theta is 160. So this is x 160 over 1760. So that's what h is, right? So this is equal to mgx sine 160 over 1760, which is a fairly small angle. Now, the equation that governs this is that delta K plus delta V must be equal to the work done. So we're talking about the change, the kinetic energy here, and plus the potential energy. If it increases, this must be equal to the work done on the car. Well, what is the work done on the car? We have a driving force, but we also have a resisting force. So the work done is going to be the difference between those two, because a bunch of 700 newtons goes on fighting the resistance. Only the remainder, 1,100, will go on. Actually, will do work on the car. That's all that's available to do work on the car. So no problem. We've got that 1,100. So right, so this is a force. Work is not a force, it's an energy, but it's being applied over a certain distance. So this is the force, and work is just equal to force times distance. So this is 1,100 times x, because that's how long, we're at some point x along the ramp, and it's been exerting this force the whole time. So the work done, the net work done is 1,100x. So this is equal to 1/2 mv squared plus mg blah, 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 blah. And you can get this into a form that they've asked for, blah, blah, blah. Oh yeah, they have specified that this is for while you're still on the ramp. That's what this means. So x is less than 1760. And that's important because once you get to the top of the ramp, which is what the next question is asking for, once you get there, the potential energy no longer increases. So all of the work done is increasing the velocity. So let's just move this here. So this is for question 1. So for question 2, it's really pretty much exactly the same thing. So question 2, we've still got that the contagion kinetic energy is the same with some v squared, which we're sort of giving an equation for. Delta v now is just, it's a delta v between the bottom of the ramp and this top. So it's reached a maximum. There is no more additional gain in potential energy. So we know the height, it's 160 meters. So we get, it's 160 mg. And then we plug this back into the equation. We have the same amount of work done. It's 1,100 x, because x includes all the way up here, and maybe now it's sitting here. So now x is this whole distance, but it's still the length of the distance that along which the force has been exerted. So that's still the net work done, is equal to the kinetic energy. So it's going to be 550 v squared plus this change in potential energy. And if you manipulate this very lightly, you will get this equation. Okay, pulleys. Everyone loves them. These kinds of questions, they always rely on the fact that the tension in this string is the same as the tension in that string, and that the acceleration, this acceleration is the same as this acceleration of the objects. So this is all you need to know to solve these equations. But let's just go into a little more detail. So let's split this up into 2 different diagrams. So we can just think, what is happening to A on its own? Well, it's got MAG acting downwards, and it's got T acting upwards. And we have exactly the same diagram for B, except with MBG. And at the beginning, they're held still, but then they're released and they move. So I'm going to use, my little convention I'm going to use for this question is that positive motion is defined as going up here and across down there. So it's sort of this kind of movement of the string, which is the way it's going to move. So it's useful to me to define that as positive. So in this diagram, we're going to use Newton's equation. F is equal to ma, Newton's second law. So the force on A, this is just, well, I'm defining this as positive, right, going upwards. So T minus mag is the net force. And this is equal to mass of A times the acceleration A. What about this guy? Well, the force on B, I'm defining downwards for B as being the positive direction. So this is mbg minus t, and this is equal to mba. So now I have these two equations, this one and this one. If I add them together, I will get, if I add them together, the t's will cancel. So I get mb plus, mb minus ma g is equal to ma plus mb. Oh my goodness. mb. Forgive that. Don't know what's going on there. Oh. mb, come on. Times a. Anyway, you know what I'm saying. We know mb, we know ma, we know g. We can solve for a. And we happen to get 5 meters per second. So that's the acceleration of a, and also happens to be the acceleration of b. And they want the distance traveled by a before the string breaks. So we don't know anything about like the strength of the string or anything horribly complicated like that. We're just told that it breaks 0.6 seconds later. Well, in that case, we have all we need. We have a distance, and that is going to be equal to the initial velocity times the time plus 1/2 times the acceleration times the time squared. And in this case, that's equal to 0 plus 1/2 times 5 times 0.6 squared. So it's no problem to get the distance. Okay, sub-question 2. So here we've got a velocity time graph. And this question is really about you being able to interpret it and not getting confused and thinking that it's a position time graph. So don't think that this point represents the highest that the thing is going. It's just the highest velocity. So what here they're even saying, so this is when the string breaks. Let's write that down. String breaks. So it's been accelerating upwards, right? At some point the string breaks, so it stops accelerating upwards. You know, there's no force on it to accelerate upwards. It actually starts decelerating, being accelerated downwards by gravity. So therefore its velocity will go down. But it still takes a while for its velocity to slow to 0, right? So it's still heading upwards for a while. So it's only over here that it reaches the top of its trajectory. It's only here that the velocity decreases to 0 and then starts increasing downwards. And so you have this motion downwards. So this is actually the highest it will be at this time t. So let's look at those times. We need to find the value of the velocity at the time the string breaks and when the motion is at its peak. So v is pretty easy. We have v, and we remember the constant acceleration equations, and this is a constant acceleration. So it's v naught t v naught plus a t. Well, v naught is 0, so it's plus 5 times 0.6, which is 3 meters per second. No problem. And then we need to find t. So consider what the velocity is at this time. Well, it's the peak of the motion, right? The velocity is always 0 at that peak because it's the point at which it stopped moving upwards and starts moving downwards. It passes through like complete stillness at that moment. So at t is equal to t, v is equal to 0. So we can use this piece of the motion to analyze what time, like how long it takes, basically. We know what the acceleration is after the string breaks. It's just gravity. That's the only force on it. So we know the acceleration, we know the initial velocity, we know the final velocity, 0. Therefore, we can work out the time. So we have final velocity is 0. That's equal to the initial velocity minus g t, because it's the same, it's this exact same equation, but the acceleration is minus g because it's acting against, we're talking about the up being positive. And this you can just solve. Oh, my mistake. This is actually not t. Well, okay, it's t. It's this time, right? So it's the amount of time between this point and this point, which is big T minus 0.6. And so you can just solve this for big T. Now what they want is, okay, distance traveled. So this is knowing the fact that on a distance time graph, the area under the line is the distance traveled in that time. So this is now, usually these will often be, in general, these will be like curves and you have to integrate. But in this case, it's super simple. They're nice crisp triangles. So you just apply 1/2 times base times height. So let's look at how much it's traveled upwards. Well, that's just 1/2 times 0.6 times 3, which is the height, 3, v, plus 1/2 times t minus 0.6, that's this base, times the height again, which is 3. And that's the distance traveled upwards. Distance traveled downwards, now they haven't given you what the velocity is at the bottom when it hits the floor. So don't bother, you can work it out, but like it's much better just to use the constant acceleration equations again. So you've got, we know the velocity at this time. And so we have that we're looking at the distance traveled, and we know the acceleration, it's just gravity again. So the distance traveled here, well, this is just S is equal to V at time t plus 1/2 g t squared, because we're thinking of gravity sort of like increasing the distance because we're going downwards now, so we're giving it a positive. Well, velocity at time t is just 0. So this is going to equal to 1/2 times 10 times this time, which is just 1.6 minus t, all squared. So that gives you the full distance traveled downwards. So therefore we can find out the height. Like, that's super simple. We start over here, we go up a certain amount, and we go down all this amount. Well, it's just going to be the difference between that, isn't that? That's h. Okay. This question is sort of focused on differentiation and integration, and it's sort of asking you to be a little careful. So there is not always constant acceleration in this question. So, well, let's start at the beginning. We have some kind of two cyclists traveling A to B to C, and they arrive at each one at the same time. But that's not to say they travel together. They start with different velocities, they end with different velocities, they do funky stuff in between with acceleration. So, but they do happen to pass this one at t is equal to 0, and this one at t is equal to 400 seconds, and this at some later time. So let's look at cyclist Q. We want to show that the distance from A to B is 1,600 meters. So, and what we're given is cyclist P starting with 3 meters per second. So let's say question 1, P. So the information we have from him, we have his initial speed, and we have that he has a constant acceleration. So easy. AB is just initial velocity times time plus 1/2 times acceleration times t squared. We know V naught. We know t was given as 400 seconds because this is when he's at point B. We know the acceleration, and we know t again. So we can easily get this number. And then we're asked to find his speed, or her speed. And we can again just use that v at b is equal to the initial velocity plus acceleration times time. So we have the initial velocity, we have the acceleration, we have the time. No problem. Now they're talking about cyclist Q, and he's doing something a little more tricky. So he's got this differential equation, this equation in time. And you notice that this is not a constant acceleration he's going. Because remember, constant acceleration equations, the velocity is something like this. V is equal to A plus BT. It's a linear equation where this is going to be the acceleration, this is going to be the initial velocity. This has a t squared term. So something funny is going on with the acceleration. Basically, it's not constant. The acceleration is a function of time. It's changing. So we just have to be a little more careful. The first thing, so we asked to find k. And we're not really given, we can't really use boundary conditions from what they've given us yet. So the first thing we're going to do is integrate. So v is just equal to dx dt, right? So therefore, if we integrate both sides of this, we get that x is equal to 0.02 t squared minus 0.0001 over 3 t cubed plus kt plus c. At first, this looks like bad news. I mean, we've got another constant coming in here that we have to find. But actually, we can immediately use a boundary condition, which is the fact that at the time equals 0, the position was 0. The guy hadn't moved at all. So therefore, all these terms go to 0. Therefore, c must go to 0. So there is no constant term. Great. We also have the boundary condition. So we used the boundary condition that x of 0 is equal to 0. X at time equals 0 is 0. And we also have the boundary condition that x at time 400, well, at 400 seconds, he's at B, which is at 1600 meters. So if we plug that into there, we can get k. We have t, we have x, we work it all out, and we get that k is equal to 4/3. Well, great. So we've done our integration, and we found the value of k. Now we need the maximum speed of q before he's reached B. Well, what do we do when we look for maxima and minima? We differentiate, of course. So we integrated this equation to find out what k was. Now we're going to differentiate this original equation. So we're going to find the acceleration, because the derivative of the velocity is just acceleration. So I'm just going to get this out of the way a little. I hope it's still readable. Okay, so now we can look at dv dt, and we say that at the max speed, this is equal to 0. That's the simple fact. The first derivative is equal to 0 because your velocity is peaking over here, and the slope therefore is flat. And if you just solve this, you will get a time, and then if you plug that back into the original equation, you will get Vmax. Okay, last section, last question. Find the time taken for the cyclist to travel from B to C, and then find the value of A. So this has got two bits. The first part, it's much easier just to use the cyclist P, because as we see here, he's now traveling at a constant speed. So he accelerates, and this is cyclist P. He accelerates until he gets to B, and then he just stops accelerating. So a constant velocity is a joy because we don't have to worry about it. So let's just look at cyclist P again. The distance he travels, S, is 1400 for both of them. And this is equal to V0 times the time that it takes him from B to C, plus no acceleration, no accelerating at all. So if you solve for this, you get t is equal to 280 seconds. So this is from B to C, not the whole time he's traveling. They took 400 seconds to get to B, and they take 280 seconds to get from B to C. Now, if we want to find A, obviously we have to look at cyclist Q, who's accelerating at A. So for cyclist Q, we know that he must have also taken that many seconds, because we know they both reached B at 400 seconds, and they both reached C at the same time. So they must have both taken 280 seconds. They must have both reached there at 680 seconds. So the distance traveled, which again is 1400, same distance, is the velocity that he had at B at t is equal to 400 seconds. So the velocity at that point times the time from B to C plus 1/2 a t squared. Well, we have everything in this. The velocity at time is equal to 400 seconds. We just get from this equation here. We just plug in 400 seconds. We know k. And then we will get that this is equal to 4/3 t plus 1/2 at squared. And there we go. That's all we need. We just t we know is 280 seconds. So we get a that way. And that's all there is to it. Please let me know if you have any questions.